On July 3, 2025, the Vera C. Rubin Observatory photographed an object that nobody on the science team was actually looking for. At the time, the telescope was still deep in its commissioning phase, running calibration tests, checking instruments, doing the slow, careful work of making sure every system functioned correctly before its real 10-year survey ever officially began. Nobody was searching that specific image for anything unusual at all. It simply sat there, in the observatory's growing archive, an ordinary calibration frame among thousands of others. It would be nearly a year before anyone realized what was actually hiding inside it. A genuine interstellar visitor from beyond our solar system, captured on camera before almost any other telescope on Earth had even noticed it existed. In the months since, headlines have spread across the internet claiming Rubin's latest images contain something impossible, something unexplained, even something suggesting alien activity. Almost none of that is true. But the real story, once you set the exaggeration aside, is genuinely remarkable enough to be worth telling properly. This is what Vera Rubin Observatory has actually captured, why some of it looked mysterious at first glance, and why the actual explanation turns out to be more impressive than the myth. To understand why an object could sit hidden in the observatory's own archive for nearly a year before anyone noticed it, you first need to understand what Rubin was still in the middle of doing back in July of 2025. The observatory had unveiled its first public images only 2 weeks earlier, on June 23rd, revealing a facility built around the largest digital camera ever constructed, a 3,200 megapixel instrument capable of photographing the entire visible night sky in extraordinary detail. But revealing those first images was not the same as beginning the observatory's real mission. Rubin spent the following months in a careful, methodical commissioning process, testing its instruments, refining its enormous data processing pipeline, and specifically, at that early stage, the automated software responsible for identifying and tracking fast-moving solar system objects. Asteroids, comets, and anything else drifting quickly across the sky was not yet fully operational. That detail matters enormously for this story because it means when Rubin's camera happened to capture an image containing a genuine interstellar comet on July 3rd, 2025, none of the automated systems built to flag exactly that kind of object were actually running yet to catch it. The object in question had already been independently discovered by a separate survey called the Asteroid Terrestrial Impact Last Alert System on July 1st, 2025, and formally designated 3I/Atlas, only the third confirmed interstellar object ever detected in the history of astronomy. A genuine visitor from another star system passing through our own on a one-way trajectory that will eventually carry it back out into deep space, never to return. Once astronomers around the world began intensively studying this rare object using telescopes ranging from Hubble to the James Webb Space Telescope, a natural question arose. Had any other observatory happened to photograph this same object earlier, before its official discovery, without anyone realizing it at the time? A research team, led by astronomer Colin O'Ryan Chandler, set out specifically to check Rubin's own early commissioning archive for exactly this possibility, and in a paper published in May of 2026, they confirmed it. Rubin had indeed captured the comet on July 3rd. Sitting quietly in calibration data, nobody had originally been searching for anything of scientific significance at all. Because the observatory's dedicated pipeline for tracking fast-moving objects was not yet running at the time, Chandler's team had to develop entirely custom analytical techniques just to properly extract useful, precise measurements from this unplanned, essentially accidental observation. Their effort paid off considerably. Despite the challenging circumstances, the team successfully measured the comet's precise position, tracked its brightness, refined its calculated orbit, and even studied the physical structure of its nucleus and surrounding coma, extracting genuine, useful scientific data from an image that had originally been captured purely to test whether the telescope's own instruments were working correctly. This is, in its own way, a remarkable demonstration of exactly the kind of capability Rubin was specifically built to provide. An instrument so relentlessly thorough in photographing the sky that even its own routine calibration exercises end up accidentally capturing genuine scientific treasures, simply waiting for someone to eventually go back and notice them. This kind of retroactive discovery, astronomers going back through an archive to find an object that had already been sitting there unnoticed, is common enough in the field to have its own specific name, a pre-covery, short for pre-discovery observation. Pre-coveries matter enormously for a genuinely practical reason, one that goes well beyond simple curiosity about whether a telescope happened to catch something interesting before anyone realized it. The precision of any calculated orbit for a newly discovered object depends heavily on how long a period of time astronomers can actually observe that object across. A comet or asteroid tracked for only a few days produces a comparatively rough, uncertain orbital estimate, since there simply is not enough data yet to fully constrain exactly how its path curves through space. Every additional observation, especially one stretching backward in time before the object's official discovery date, tightens that estimate considerably, allowing astronomers to predict its future position with far greater confidence. In the specific case of 3I/Atlas, an interstellar object that would only remain observable for a limited window before leaving our solar system forever, every single day of additional tracking data mattered enormously. And Rubin's accidental July 3rd observation, once finally recovered and properly analyzed nearly a year later, extended the total observational baseline for this rare object meaningfully, helping refine exactly the kind of precise trajectory calculations researchers needed to plan follow-up observations using other telescopes around the world. This pattern, genuine, quietly extraordinary discoveries, hiding inside data that looks unremarkable at first glance, has continued well beyond that single comet sighting. In January of 2026, astronomers analyzing Rubin's data announced the discovery of the fastest spinning asteroid larger than half a kilometer across ever recorded, a small world completing a full rotation roughly once every 113 seconds, spinning so rapidly that it sits right at the theoretical edge of what a loosely bound pile of rubble can withstand before centrifugal force would begin tearing it apart entirely. Researchers studying this object have noted that finding an asteroid spinning this close to its own structural breaking point provides genuinely valuable information about what these small bodies are actually made of internally, whether they are solid, coherent chunks of rock or loosely assembled piles of rubble held together by comparatively weak mutual gravity, information that becomes considerably harder to obtain through any other observational method available to astronomers today. This particular asteroid, formerly designated 2025 MN45, was actually first captured during Rubin's original First Look program back in the spring of 2025, part of an early batch of nearly 1,900 asteroids the observatory identified during just a few weeks of preliminary testing focused on the Virgo cluster, long before its full survey had even begun. Astronomers were only able to determine its remarkably fast rotation because Rubin happened to photograph the same small patch of sky repeatedly over a short span of time, catching the asteroid's brightness rising and falling as its irregular shape rotated in and out of view, a pattern that would have been essentially impossible to detect using a telescope that only glimpsed this particular object once or twice. This is precisely the kind of discovery that depends entirely on an observatory's capacity for repeated, systematic imaging, rather than any single, well-timed photograph. Exactly the observational strategy Rubin was built around from the very beginning. Object rotation speeds like this one matter to planetary scientists because they help establish what is sometimes called the spin barrier, the theoretical rotational speed beyond which a rubble pile asteroid, held together by nothing more than the weak mutual gravity of its own loosely bound fragments, would simply fly apart under its own centrifugal force. An asteroid spinning this close to that limit, while still remaining intact, suggests it may possess at least some internal cohesion beyond pure gravity alone, perhaps weak but real structural bonds between its component rocks, a genuinely useful data point for scientists trying to understand the internal structure of small solar system bodies without ever needing to send a spacecraft to physically sample one directly. Beyond individual discoveries like these, Rubin has also spent the first half of 2026 building out an entirely new kind of infrastructure for astronomy itself, one specifically designed to make sure genuine discoveries do not sit unnoticed in an archive for months, the way that Interstellar Comet initially did. On February 25, 2026, the observatory issued its first live scientific alerts, a historic milestone mission scientists described as the beginning of a genuinely new era of dynamic, real-time observation of the night sky. Rather than simply storing images for researchers to review later, Rubin's software now automatically compares each new photograph against previous images of the same patch of sky, flagging anything that is visibly changed, brightened, dimmed, or moved, and immediately alerting astronomers around the world so that other telescopes can follow up before a fleeting event fades away entirely. Once fully operational, the system is expected to generate as many as 7 million individual alerts every single night, an almost incomprehensible volume of real-time information that no previous observatory has ever come close to producing. In March of 2026, NOIR the organization operating Rubin, completed a series of successful end-to-end tests of the entire follow-up system supporting this alert network, demonstrating how a coordinated web of software tools and telescopes scattered across the globe will be able to respond quickly to whatever Rubin's cameras happen to catch each night. The same infrastructure connects directly to one of the more genuinely exciting frontiers in modern astronomy, a field called multi-messenger astronomy, which involves studying a single cosmic event using several completely different types of signals at once: ordinary light, gravitational waves rippling through space-time, and high-energy cosmic rays, each one capturing a different piece of the same underlying story. Rubin's rapid, continuous, color-rich observations of transient events, exploding stars, actively feeding black holes, and even the aftermath of collisions between extraordinarily dense objects like neutron stars are specifically intended to help guide other telescopes and instruments around the world toward exactly the right patch of sky at exactly the right moment, turning a brief, easily missed cosmic event into a thoroughly documented multi-instrument scientific investigation. None of this represents an unexplained mystery in any sense. It represents something considerably more valuable, a genuinely new scientific capability, built specifically to make sure the universe's most fleeting, most easily overlooked events finally get the sustained attention they deserve, rather than simply ignoring them. Because separating real discoveries from manufactured hype is exactly the kind of clarity this story deserves. Several corners of the internet have specifically promoted the idea that Rubin's images contain unexplained objects, impossible phenomena, or even hints of alien activity, headlines that generated considerable attention without actually pointing to any specific, verifiable finding matching that description. This is worth stating plainly. Nothing in Rubin's published, peer-reviewed observations to date has revealed anything genuinely inexplicable by ordinary astrophysics, let alone anything suggesting extraterrestrial technology. What Rubin has actually revealed repeatedly is considerably more grounded and, in its own way, more genuinely exciting. An instrument so comprehensive and so relentlessly thorough in its coverage of the sky that it keeps finding real, previously unknown objects and phenomena simply because nothing quite this systematic has ever been pointed at the entire visible sky before. This distinction matters because it reflects something genuinely important about how real scientific discovery actually tends to work, as opposed to how it gets portrayed in more sensationalized coverage. Rubin was never built to find any single, isolated, dramatic anomaly. It was built to systematically photograph the entire visible southern sky, over and over, roughly every few nights, across a full 10-year survey called the Legacy Survey of Space and Time, which officially began its complete operational phase on June 30th, 2026. It is also worth understanding exactly why headlines promising unexplained or impossible imagery attach themselves so easily to a project like Rubin in the first place, since that pattern is not unique to this specific observatory. Anytime a genuinely new, extraordinarily powerful scientific instrument comes online, producing more data in its first year than most entire previous surveys managed across their whole operational lifetime, a predictable cycle tends to follow. Genuine, interesting findings, a fast spinning asteroid, an accidentally recovered interstellar comet, get reported accurately by the scientists and institutions actually involved. Those same findings then sometimes get picked up by less careful outlets, stripped of their specific technical context, and reframed using considerably more dramatic language than the underlying research paper ever actually supported, since vague, mysterious-sounding claims tend to travel further online than careful, appropriately qualified scientific descriptions ever do. This is precisely the pattern behind claims of unexplained or impossible imagery attached to Rubin's genuinely real, but genuinely more modest, actual discoveries. The corrective is not to stop paying attention to what a new instrument like this actually finds. It is to keep checking those claims against what the researchers and institutions directly involved have actually published and stated themselves. Exactly the kind of verification that reveals the real story behind Rubin's images is compelling enough on its own, without needing any invented exaggeration attached to it at all. Rubin's own science team has described the underlying philosophy behind this approach directly, explaining that some cosmic processes unfold slowly, unpredictably, or incredibly rarely, which is exactly why a survey spanning an entire decade is genuinely necessary to catch them at all. The observatory is currently producing a new image roughly every 40 seconds throughout every clear night, systematically building what researchers have taken to calling, without much exaggeration, the greatest cosmic movie ever made, an approach specifically designed to catch precisely the kind of rare, fleeting, or previously unrecognized phenomena that a single, one-time photograph would almost certainly miss entirely. The same systematic, comprehensive approach is precisely why Rubin is now positioned to potentially resolve several of the biggest open questions in modern astronomy, questions considerably more scientifically significant than any manufactured claim of impossible imagery circulating online. Chief among these is the decades-long search for a hypothetical ninth planet, a large, undiscovered world some astronomers believe may be orbiting far beyond Neptune, its gravitational influence inferred from subtle patterns in the orbits of smaller, more distant Kuiper Belt objects, but never yet directly observed. Alex Jerlicka-Wagner, an astronomer involved with the Rubin mission, has explained that if this hypothetical planet genuinely exists, Rubin's systematic repeated coverage of the sky gives astronomers a realistic chance of actually detecting it directly, something no previous survey has managed despite years of dedicated searching. Rubin is also expected to substantially expand the catalog of confirmed interstellar objects passing through our solar system. with some researchers estimating the observatory could detect anywhere from 5 to 50 additional interstellar visitors over its full decade-long survey. A dramatic increase from the mere 3 confirmed examples found by all previous astronomical efforts, combined across the entire history of the science. And underlying all of this sits the observatory's most fundamental scientific purpose, one directly connected to the astronomer this facility is named after. In the 1970s, Vera Rubin herself discovered that stars at the outer edges of galaxies were orbiting far too quickly to be explained by the gravity of visible matter alone, evidence that ultimately became some of the strongest support for the existence of dark matter, an invisible substance that we now believe makes up the vast majority of all matter in the universe. Rubin Observatory's entire 10-year survey is specifically designed to extend that same basic investigation to an almost unimaginable scale, using the exact same fundamental principle Rubin herself relied on. That unseen mass reveals itself through its gravitational effects on the things we actually can see, including the way it subtly bends and distorts light traveling toward us from galaxies scattered throughout the observable universe. Dr. Lika Wagner has described this specific technique directly, explaining that dark matter bends light as it passes by, distorting the appearance of a distant background galaxy, and that Rubin will collect enormous numbers of these subtly warped images, allowing scientists to map out where dark matter actually sits throughout the universe based purely on how it visibly bends the light passing near it. This effort builds directly on groundwork laid by earlier surveys that Rubin is now positioned to dramatically surpass. In January of 2026, the Dark Energy Survey Collaboration published its own culminating analysis, built from years of observations, covering hundreds of millions of galaxies using a specialized camera mounted on a telescope in Chile, providing some of the most precise measurements yet of exactly how the universe's expansion has evolved over cosmic time. That entire survey, spanning years of dedicated observation, covered a meaningful but comparatively modest portion of the sky compared to what Rubin alone is now expected to accomplish. Over its own 10-year run, Rubin is projected to observe roughly 20 billion galaxies in total, an enormous leap in raw statistical power that should allow researchers to test the exact same fundamental questions about dark energy and cosmic expansion with considerably greater precision and confidence than any previous survey, including the Dark Energy Survey itself, has ever been able to achieve. Dark energy, the mysterious force apparently driving the universe's expansion to accelerate rather than slow down over time, was first confirmed back in 1998. And it remains, alongside dark matter, one of the most significant unexplained problems in all of modern physics. Precisely the kind of genuinely open, scientifically important mystery that deserves the word unexplained considerably more than any invented claim about strange objects hiding in a calibration photograph. So here is the honest, complete picture behind what Vera Rubin Observatory has genuinely captured so far, laid out plainly rather than exaggerated into something it is not. There's no verified evidence of anything impossible, inexplicable, or artificial hiding in its images. What genuinely happened is considerably more grounded and arguably more impressive on its own merits. A telescope, still in its early commissioning phase, running routine calibration tests, accidentally photographed a genuine interstellar comet nearly a year before anyone realized it was sitting there, hidden in plain sight, waiting for the right researchers to develop the right techniques to finally notice it. That same observatory has already identified the fastest spinning large asteroid ever recorded, and it has only just begun its full official 10-year survey, a systematic, relentless effort to photograph the entire visible sky over and over, specifically designed to catch exactly the kind of rare, fleeting, previously unrecognized phenomena that no single observation could ever hope to reveal on its own. That is the real story, and it does not need any invented mystery to justify the attention it deserves. An instrument this comprehensive, watching the sky this closely for this long, is going to keep finding things nobody expected. Not because reality is breaking down, but because nothing this thorough has ever been pointed at the universe before. Somewhere in the billions of galaxies, asteroids, and passing objects Rubin will observe over the next decade, genuine discoveries are waiting. Discoveries no scientist has yet predicted, hiding in exactly the same way that interstellar comet sat quietly in an unremarkable calibration image for nearly a year before anyone thought to look closely enough to find it. If you want to see what Rubin uncovers next as its 10-year survey continues, subscribe and turn on notifications, because this observatory has already proven that its most remarkable discoveries are sometimes hiding in the images nobody thought to look at twice.